So let me start recording. First of all, the announcement for the next exam was already posted on the website. So let me show it to you quickly. Let's see, it's here. No, this is not updated. Let's see. Oh, here it is. Yeah. So, yeah, so as I had mentioned, the next exam is in 2 weeks on December 6th. It's online. As before, it has two non-upload problems, two upload problems. There are like 5 practice exams posted on MyLab that you can work on. The solution for those will be posted like in a week. So they should be posted here below the study guide exam. And then, well, you can read the announcement. Basically, these are like the exam. Essentially, today we'll finish up to this section 16.4. So this will be the last section that we covered today. As you know, we don't have classes on Thursday because of Thanksgiving. And then next Monday, we also don't have classes because of this like weird calendar thing that they do. So really like the we'll meet is like on Thursday of next week, and that's when we will do 16.5. So what I will do is that I will also I will post a video from last semester when I taught this section in previous class, in case you want to watch it during Thanksgiving break and just have like, just know the last topic for the exam before during Thanksgiving. But in any case, we will cover it. But I'll just give you that option to watch the video from last semester in case you just want to like be done with the material for this exam. Okay, so that's basically so today what we have to talk about mostly is about Green's theorem and a little bit about flux, so which I haven't discussed. So let's maybe we should get started with that. So finally, we're almost reaching the end of the course. So it's time to discuss the calculus triforce. For those of you who like Zelda. So essentially, there are like 3 main theorems left in this class. One is Green's theorem, the other is Stokes' theorem, and the other is Gauss's theorem, also called the divergence theorem. And so what we're going to talk about today is that we're going to talk about Green's theorem. And you'll see that essentially there are 2, like Green's theorem is like basically for, it's on the XY plane. Okay, and so there are 2 ways to sort of generalize Green's theorem, or like there are 2 versions of Green's theorem, and one version becomes Stokes' theorem, and the other version becomes Gauss's theorem. So essentially what we're going to do today is like just like study this version for the XY plane, and then next after the break we'll like cover like its generalizations to 3 dimensions. Okay, so this is like in 2 dimensions, and this row, and this is in 3 dimensions. Okay. So before that, maybe, and again, like we don't have too much time left, so unfortunately, I'll just have to give you a couple of black boxes. Although like some of more explanations can be found on the YouTube videos if you feel like watching those. But I don't know if you remember last time. Last time, oh, it's the announcement was posted on, it's on the website. So it's basically, if you go to the department website, you can find it here. So, oh yeah, I forgot to say that. I'll post the grades probably the latest on Wednesday, or if not tomorrow. So you'll have your grades either Tuesday or Wednesday before the Thanksgiving. What I'm not 100% sure is if the letter grades will be like, I'm waiting just to see if we have enough, if all the grad classes have graded by then, and so that I can give you like the letter grades as well, and not just your like numerical grade. But at least your numerical grade, you'll have them by tomorrow or Wednesday for sure. And like the letter grades would then maybe be sometime later this week, but it went well. Yeah, yeah. Yeah, the letter, that's the thing, right? Like the letter grades, like look at all these sections, correct? So that's why usually that takes a little bit more time. Good, good, also, well, good, yeah. So, so the last time what we did was like, we were talking about conservative forces or fields, vector fields. So remember that if we had like a force F or vector, right? If the curl of F was vanishing, right? Which means that this was 0, which means it was a vector 0, 0, 0, right? We said that then F was conservative. And so that means also that you can write F as a gradient of some function, right? So F was a gradient of some function, little f, which this was called the potential, right? And the whole point for doing this, like this was the key fact that we used at the end. Like the whole reason for doing this is that if you choose a path, say from a point P to a point Q, you choose your favorite path connecting those 2 points. So something weird. Okay, just like imagine like a weird trajectory. Okay, then the work in the conservative case, let's call this trajectory C for curve. So the work, which is how this, remember, is like the way in which usually work is written. So this means the work from going from P to Q. If you remember, if you have like a conservative force, it's just like the difference in the values of the potential function. So it's just you evaluate the potential function at the endpoint, at the final point, minus the potential function at the initial point, and then you just get that. So again, this is very important, like just for conservative forces. The color red is a complete accident. It was not planned. So, okay. So, so far so good. Is this okay? Now, what do you think the work would be if the endpoints are the same, meaning that if P and Q happen to agree, right? So you do like you start at a point P. Well, I don't think there's like a very intuitive explain. I mean, the definition, right? It's like that the work is independent of the trajectory that you choose, right? Like that's the actual definition of a conservative force. I don't know that's not necessarily very intuitive, right? And it's a little bit circular, but like you could also think of a conservative force as being one where like no, if you thought about it more like in physical terms, where there will be like a conservation law, because that means like energy will be conserved because of this like potential function that you find. So, which again, like it may not be like that intuitive, right? But yes, good. If you, as I was trying mentioning, if you choose like a path that is a closed path or like a closed trajectory, right? A closed loop, or maybe that's a little bit redundant, but like a closed path, meaning that like you end where you started, right? You're doing like a round trip, right? Then the work should be zero, right? For like a conservative force, right? Because you're evaluating the potential at the same, the potential at the final point is the same as the initial potential at the initial point, right? So P equals Q in a sense, in this case. So here the work for a conservative force is zero. Is that making sense? So what so far so good? So when you can think of here's the cool thing. So in the case of a wire, right, a closed loop, we know then like what the answer, what the work is for, yeah, here's a closed loop, right? In the case of a wire or something that closes, we know the answer for of what work is for conservative forces is quite easy, right? Because it's just zero, the work is just zero, right? But the next theorem is called Green's theorem, and it gives you like the formula for what the work is in the case of a closed loop, not just for conservative forces, but for any force. So that's what we're going to talk about right now. So here's Green's theorem. Again, like we'll state it just first for regions on the XY plane, although later it will become like, you know, again, like after the break, we'll generalize this. So, and like, well, let me write it. So what Green's theorem says is that if you have for regions on the XY plane and for curves which are close, well, I'll write it here in this statement. So what Green's theorem says is that if C is a closed curve, and this is very important. Again, it has to, you have to close it up. It has to go, I mean, the initial and the final point need to be the same, right? And R is the region it encloses. Then the work done by a force or field or vector field F along the curve equals the following. So let me, you do have recitation tomorrow. Yes, there's a quiz. Let me do a picture first. So what I'm saying is that imagine that you have some closed curve like this. In fact, you can make it like you can make it like fun or what, like I'm trying to was trying to draw Mickey or Minnie, but it, okay, like that's not yes, it's more like a something amorphous, but it's a closed curve, right? And so being closed, it encloses something, right? So this is the name for the curve, and being a closed curve, it does close up a region, right? Think of it like that, this curve as some sort of border or frontier, right? So this is like the region that it encloses. Right? So this is like what I'm calling R. Yeah, we do have recitation tomorrow, or you do, not me. There's a quiz tomorrow also. Yes. So what the formula says is that the work, right? Which again, this is like the notation for the work. Here, well, I'll say it in a second. It's actually like, this is a cool fact. What this is saying is that you can, instead of doing directly this integral for work, you can replace it with a double integral of the region enclosed by R. So this is like what Green's theorem, this is like what Green's theorem says, is that instead of doing the integral that we have been doing for the past few days, what you can do is a double integral over R of what? Well, I'll write it this way. Okay, you can do a double, you can integrate something like, you can do a double integral, and what you have to integrate is the dot product between the curl of F and the vector K, where K here is the vector 0, 0, 1 that you know from the beginning of the course. Okay. Okay. And then and more importantly, the curve C is being, you're moving in a counterclockwise way. For this theorem to work in the way I wrote it, the curve is traveled, or the path is traveled Usually the technical word for traveled is oriented in a counterclockwise way. For this theorem to be true. Is that making sense? Is that okay? So, but again, it's kind of like it's nice that what this is saying. This is saying is that instead of like doing directly like the integral for work, you can replace that with the double integral. And more or less what you have to integrate is like this dot product that involves the curl. The way in which you'll see it written in the book. So this is like how it appears in the book. So the book, what it does, the authors do is just write F into their components. So you write F, and I don't like this notation, but it is what it is. Well, if F in the case of the book, like you can just, you're looking like at forces that are just like on the XY plane. So that's why the third entry is 0, which is fine. And so the Green's theorem, just the curl becomes the curl of F. It's like a quick computation to do. The curl of F becomes the partial derivative of n with respect to x minus a partial derivative of m with respect to y. And so Green's theorem so this is usually the way, if you go like, you know, if you like enter Green's theorem on Wikipedia or something like that, this is typically the way in which it's written down. But that's like what you get by doing like the dot product with the vector k. Again, in an ideal world, I would tell you also why Green's theorem is true. Every time I have tried to explain this in class, it takes me like 40 minutes, which we don't can afford it right now. It's like basically what you end up doing, like in a nutshell, what you do is like you first, and I'll erase this because I don't like, it's not something to worry about, but you essentially check the theorem in the case of a rectangle. So you verify the theorem for a very small rectangle. It has to be very small so that you can do some sort of Taylor approximation or something to actually compute the work. And so in the case of a rectangle, you sort of check that this works for rectangles. And then if you have like the Shrek region, right? Or like if you have like a region which looks like a star, you sort of start breaking the whatever region you have into bunch of rectangles. So you start approximating every region by rectangles, and so you sort of get the result for the larger case, or for like the arbitrary case, by like an approximation scheme. So there's like a couple of steps involved, but again, like it's explained on the YouTube videos, but it's not something that you need to know how it's shown. It's kind of interesting, but we'll have to omit that for today. Okay. So far, so good. Are there any questions up to this point? Let me just zoom a little bit in case someone needs to write the statement. So is this okay? And also I'll put this, oops. Let's do an example.
Are the right sides of both of the boxed equations equivalent?
What about the right hand sides?
The right-hand sides of both the top and the bottom boxed equation.
They're the same thing, actually. Right.
And the bottom one is just if you carry out the cross product.
Right. Like this one is like worked. It's a little bit like worked out for you because it's just writing the curl in this part in this case. So I'm saying like, right. It's just like this is like the formula in like written like in general, but like if you work out the curl, you just get like this particular vector, and so when you do the dot product, you just get this, right? So this is like the one that you can like. This is like the like if you want like this is the version how we will use it. The thing is like give me a second. Had I shown you already this? So the thing is like eventually we'll apply like a version of Green's theorem for curves, but the curves are no longer necessarily on the XY plane. So imagine that you have like a curve, like say like the curve is in this, like the circle, right? The net. So let's say that here is like the circle is on the XY plane, right? But now it's no longer on the XY plane because I have tilted it, right? So if you want to, here you cannot really apply Green's theorem. What we have to apply is something called Stokes' theorem. And Stokes' theorem, what it says is like you have to find like a surface whose boundary is the curve in question. So in this case, you have to find like the surface could be like, for example, this net that I'm showing you. And then like the work along the circle can still be computed with the formula that I wrote in the first box. But instead of using the vector k, you have to use like the vector that's perpendicular to the surface. I don't know if you remember like when we found tangent planes to surfaces that we talked about like a normal vector to a surface. And so that's the one that appears in replacing k. The thing is like when the surface, like the curve is on the xy plane, you can always choose the vector k as being perpendicular to the surface. Is that making sense? But good. So I just wrote it in this way because this is like sort of the version that generalizes more straightforwardly to the case of curves like in space, not just like on the xy plane. But like for like at least for the next exam, for the one in 2 weeks, you can always use the formula in this version because that's all that you need. So let's do some examples. And like you might say, what's the importance of like having Green's theorem? And so let me show you what you gain from it. Let's say that f, right, it is x squared plus e to the y, comma x plus y, comma 0. That's the formula for f. So again, in comparing it with what I just wrote, this is like the first entry is in the book or almost anywhere is called M, and the second entry is called N. Okay, and let's say that I want to find the work done by F along a particular curve, and the curve that I'm going to choose is the following. So my curve is like the sides of a triangle, where the vertices are 0, 0, 1, 0, and 0, 3. Okay, so like the curve C is like the size of the triangle, and the region R is like the interior or the inside of the triangle. Is that okay? So far, so good. Now, so back in the good old days, if you had wanted to find the work, right? What is the work done by F? If you didn't have Green's theorem, right, you would have to do like 3 integrals if you think about it, because you have to do like the integral. Maybe you have done like problems on MyLab where something like this happens. You would need to do like the integral for this side, then for the hypotenuse, and then for the other side, and then you have to add up the answers, right? In fact, we had done something similar a while ago. So if your curve like sort of breaks into mini curves, right, you sort of have to find the work along each mini curve and then add up the answers. So really you're doing 3 integrals in this example if you want to do it directly. So like that, so if you do this directly, you have to do 1 integral per for each side. So that means it's 1 integral for each side of the triangle. Is that making sense? And then add up the answers. But if you are using Green's theorem, right? But with Green, you know that the work, in fact, equals the double integral over the region of this thing that I wrote before. And that's it, right? And so let's try to what does the partial derivative of n with respect to x becomes? What's the first term here? It's just 1. Good. What's the partial derivative of m with respect to y? Well, it's e to the y, right? Because the derivative of the exponential is the exponential. Yes. And it's a double integral, and you saw many of them, of these last exam. So you just have to set up the bounds. So let's say that you want to use the order dy dx, right? So if you do dy dx, remember that means that you're using vertical arrows. So what would the bounds be for y in this case? What do we put in the here in the lower bound? 0, right? And what's the top for y? It's the equation of the hypotenuse, right? So the equation of the hypotenuse is actually 3 minus 3x, because like the intercept is 3, right? So you had the slope correct, but it is, yeah, you have to, don't forget the intercept. So it's 3 minus 3x, right? And then the integral goes from 0 to 1, right, for x, because those are like the vertices of the triangle. Is that making sense? And so, and that's, I mean, that's a number. Like now at this point, you just like integrate it in the traditional way, right? And so you'll get, after you do the integral, you should get something like this. So you can check that that's the right answer. But you see, like the whole point of Green's theorem in this case was that you can replace like doing 3 integrals with just doing like a single double integral. So that's kind of cool, right? And like double integrals are things you're familiarized with. In fact, if you think about like doing work by definition, using the definition, is kind of long because you have to parameterize each segment. You know, you have to parameterize the curve, you have to find the velocity vector, you have to do the dot product with the force, then you have to integrate that. So there are many steps involved, but here's like a lot more like direct, right? Like you just compute this difference of partial derivatives and then integrate that. Good. Is that making sense? Okay. And like, in fact, they're not like any example that you see of Green's theorem is basically of this sort. So you're given like a force at a region on the XY plane, and then you just have to like, you know, set up like do the corresponding double integral. So then like the Green's theorem problems are really double integral problems. So I don't like, at least for now, I won't do more examples because I want to finish like, there's another version of Green's theorem which I want to finish today, so that we just leave 16.5 for next week, the last section for the exam. So let me do like the second version of Green's theorem. So there's like an alternative version for Green. And that involves the concept of flux, which we haven't discussed. So flux and second version of Green. So let's do an example. Imagine that anyone remembers the name of the river in New Brunswick?
Is it Raritan?
Good, good. So imagine in a not so distant future, like, I don't know, a lot of cargo shipments go through the Raritan because of the supply chain problems, and one was carrying oil, and so you have like an oil spill on the river. So like it's spreading, right? Like there was a place in the river where the leak happened, and now it's like spreading all over the river. So they're like, you know, at some time, like you have like all these like oil. Right, and you unfortunately thought that it was a good idea to swim on the river, right? And you're trying to escape you don't want to get poisoned. So you're trying to swim and to get away from this. So in order to, like, as you swim, right, when you're swimming, you swim with certain velocity, right? Let's call this velocity F, or like think of it as maybe the force that you have to do in order to escape the oil spill, right? So then you move here, and then you do something like this, right? And then finally, right? Finally, you get to say, let's say this point. Let's say that you get to this point. Now you're here, right? You're like at the border of the spill, right? Like at the frontier. You're almost like in safe waters. So you are at that point and you're going to swim. Again, you were swimming with a particular velocity. So which I'm still calling F, right? And now, I don't know, back to the first part of the semester. I don't know if you remember that we had we had seen like that a curve, right? Well, like a curve has like a vector that was tangent to it, which is more or less a velocity vector, right? So to a curve, like there's a vector, which is this red vector that I'm drawing, which is tangent to the curve. And let me draw this a little bit more, like making it look. Let me draw it like this. So you have this tangent vector, and then you have, and actually this one we didn't study, but I mean, there's on a curve on the XY plane, there's like a vector also that's perpendicular to the curve, which you may call it, if you want, the normal vector, like a normal vector, which is the one that I'm drawing here. So this is a new one. This is like a vector that's perpendicular to the curve. Okay, so just to do the picture like in isolation. So if you take a screenshot of what I'm drawing, you had like this piece of the curve, right? Like I'm zooming in this picture, right? Imagine I'm just zooming in here to show you what's going on. So when you had a vector, right? When you had a vector, I don't know if you remember, but we talked about these projections, right? Or shadows that one vector makes along another vector, right? So so you can look at the shadow or the projection, right, of F along the tangent vector, or the projection of F along the normal vector, right? There are two types of shadows you could try to compute, right? Which of the two, and that gives you two different vectors. And so which of the two do you think would be responsible? Say you got here to the border of the oil spill. Which of the two vectors is the one that's responsible for taking you, like, for finally exiting the region? If that makes sense, like which one? The one that's normal, right? Because if you just focus on the one that's tangent, like that other projection just like it's sort of like walking along the coastline, right? It doesn't, like, if you want to exit the region, like the one that will help you exit it is like the one that's along the normal vector, right? So this one is like the one that's responsible for you to exit in the region, right? So this is the one. And in fact, so like, now you could think that you were not the only swimmer. You and a bunch of other friends had decided to swim that day on the river. And then now everyone is like trying to run like crazy, to escape this oil spill. And so everyone is trying to run, or escape or swim rather. Everyone is trying to swim, but like not everyone would choose like the same spot to exit the oil spill. So some of you may reach this part, some of you may be here, some of you may be here, some of you may be here, right? So you'll sorry. So you'll reach the borders, but you reach a different border at different points. So if you want to know like the net amount of people that are exiting the oil spill, right, or the net amount of substance that is going through the frontier, what you have to do is like integrate basically this, like you have to do like some sort of integral which involves this projection vector. And so that's essentially what we're going to do next. Okay. So, and that's like what's called the flux. So like what I'm trying to say is that the flux is going to measure somehow how much things escape through a region. Okay. And so it's not like, it gives you like some sort of mass per unit time that's escaping through a region. So so let me give you the formula for flux. So this is like, but sometimes people don't forget things if there's some tragedy involved. So maybe this will help you keep this in mind. So the flux, it tells you how much stuff, like heuristically, it tells you how much stuff exits a region on the xy plane through its border. Okay. And so in fact, like the way in which it's like, again, it's something one can check, but like the idea is that if you have the curve, if this is a curve C with equation R of t, which is x of t, y of t, okay? I mean, it's again, like, it's the issue is that like there's certain sections of the book that we didn't cover, like normal vectors and binormal vectors, but one can check. I mean, there's this formula. It is possible to check that the formula for this normal vector to the curve is actually given by dy dt minus the x dy. Okay, so that's like if you have a curve and you want to compute this vector that's perpendicular to the curve, this is like one formula that you can use for finding it. And so the flux is just going to be, and so the flux is just essentially the integral, like the flux of a vector f, is going to be the integral of f dot n dt. Okay. And so let me call this big N, sorry, just to use the same notation that I used in my notes. It doesn't matter too much. Oh yeah, it's that. So it's just yeah, that's it. So I'll just write it like this. Okay. So like, how does that compare? How is this different from the formula for work that I gave you? Like the difference is that the formula for work used the dot product with the velocity of the curve, and this formula for flux uses the dot product with the normal vector of the curve, right? Is that clear? So the difference with the formula for work, so here we use the dot product with the normal vector instead of the velocity vector. Because again, the velocity vector is the one that gets used for the work. Is that making sense? Let's do an example, but it is like, it is the same, what it is essentially the same way in which you were computing work before, but now it's like you're just taking the dot product with a different one, with a different vector. So let's do an example here. Let's say that the curve is just the circle of radius 2 center at the origin. Okay. And the force, or F, is just this F, x, y, 0. Okay. So or if, I mean, you can also like, let me just, I will write it better like this way. X I plus y j. So there's a formula for F. And so the question is how to find the flux find the flux of F. So what you need to do is first find the equation of the curve. So let's start with that. Or the parametrization. Yes, that's right. That's R equals 2, right? But remember that in a parametrization, everything has to be given in terms of T, right? So here's one way to think about it. It is like, in terms of polar coordinates, this is R cosine of theta, R sine of theta, right? But as you mentioned, R equals 2, right? So this is 2 cosine of theta to sine of theta, right? And then like theta, like at this point, it's just one variable, so you can relabel this variable T. And so the parametrization of the circle is just 2 cosine of T to sine of T. Is that making sense? So yeah, and so again, this is like x of T, and this is y of T. And so the normal vector, remember, if you look at the formula that I gave you, is dy dt minus dx t. Okay, if you go up, that's like the one that I wrote before. So it's just taking the derivatives here, and so you get 2 cosine of T to sine of T. And that's a formula for the normal vector. Is that okay? So far, so good. So it's just the same as you were doing for finding work, is that instead of finding the velocity, now you find the normal vector. But you can always find a normal vector with this formula that I gave you. And so if you do this, the flux will be what? Is the dot product of f with n dt, but that's the dot product of f, which was x comma y, with n, which is 2 cosine of t to sine of t dt, right? And so you get the integral of 2x cosine of t plus 2y sine of t dt. But I don't know if you remember, this is just like the work problems. You cannot have like the expression involving x and y, right? You have to change that into something that involves only y, only t, right? So what do you replace x with? Two cosine of t, right? And y gets replaced with 2 sine of t. Good. And what are the values for t in this integral? What would you put here as bounds? T would go from where to where? It was a circle, right? So 0 to 2 pi, because t is secretly like theta, right? And theta on a circle goes from 0 to 2 pi. So you get 4 cosine square of t plus 4 sine square of t dt. And remember, cosine square plus sine square equals 1. So you get like the integral from 0 to 2 pi of 4 dt. So that gives you 8 pi. It's just that, let me put it here. We had given like formulas for x and y in terms of when we found the equation for the curve. Yeah. We replace x and y with the formulas that appear in the curve equation. Is that okay? Which is the same that we were doing for the work problems, right? So that's it. Good. Any questions about this? No. It is not. I mean, it's just because like for a circle, the easiest thing to find the equation is like to write it in polar, right? But if it's like, you know, just as an aside, so let's say that like the curve had been like just this like parabola, right? Well, what's the equation of the curve? We have done this before, right? It would be x comma y, but y becomes x squared, right? So this is the equation of the curve, right? Is that making sense? And then like the normal vector in this case would be what? The y dt minus the x dt. So it would be 2t comma minus 1. Is that okay? So it depends, like, you know, on the context. Like the important thing is always to get the parametrization. So and once you get the parametrization, you're done. Okay.
Professor,
Yes.
I'm not clear on why, like before we use polar coordinates and here we're just replacing x with t.
Oh, because the thing, like the difference here is that like, you know, if you like the thing is like if you look at the parabola, everything is easy to write in terms of x, correct? And so that's why the easiest thing to do was to like just replace, like, you know, a parameterization requires you to write things in terms of a single variable, right? In the formula for a parabola, y is like already like a function of x. So the easiest thing to do is to write just everything in terms of x and then make x equal to t. But
Is it like based on discretion? Like in the previous example, we could have.
Right, it's up to you. Here's like, in fact, if you were in like, if you say still wanted to do this in polar, right? You would say, well, y equals x squared. So that's r sine of theta equals r squared cosine square of theta, right? And so you can solve for r here. And so you can say that sine of theta over cosine square of theta, right, equals r. Is that making sense?
Yeah.
And so if you want, you can say, well, here's an alternative. You can say this is x comma y, which is r cosine of theta, r sine of theta, right? And that's what is r is sine of theta over cosine square of theta times cosine of theta, and then sine of theta over cosine square of theta times sine of theta, right? And so this gives you r equals what? Sine, well, it gives you sine over cosine, which is this one is tangent, right? And this one is what? Tangent squared, am I correct? Is that making sense?
Yeah. I see.
And that's another parametrization, and you're totally welcome to do this one. And so this is an alternative, right? Which is valid. It's just saying that the parametrization of the parabola is tangent of tangent of t and tangent square of t. But like the question is, which ones do you prefer to differentiate if you want to find a normal vector?
Yeah.
I'd rather stick with the first option, you see.
Okay, I agree. That makes
And
sense.
then and the thing is, like, there are times where like this trick will not work. If I had put like x squared plus x, then that screws everything up, and you wouldn't be able to solve for r so easily. So you just have to adjust the parametrization to what the question, like the problem in question says. Okay.
Okay, thank you.
Good. And then So why, okay, so that's how you find flux in general. And so you see it's not too bad. It's just like the same, instead of taking the dot product with the velocity, you just take the dot product with the normal vector. And then there's a green version for the flux. And so that's what we are going to end up with today. So, I mean, usually this I would have done like in 2 lectures, and so I just had to squish everything into a single lecture. But I'm essentially I'm like, yeah, I'm saying all the details that you need to know. It's just that otherwise we would have gone a little bit more slowly. But so what Green's theorem for flux says is, again, this is for regions on the XY plane. If you have a curve, again, it's like a closed curve. And so because it's a closed curve, it encloses some region, right? So here's R, the enclosed region. What Green's theorem for flux says is that the flux, which is the dot product of F with N dt, right, over the curve, is the same, thanks to Green. And again, I'm going to use the same notation that I wrote before, where F has 2 components, and I'm going to call them M and N, so that it can be compared with the formula from before. What Green allows you to do is do like a double integral. And what you put here is a sum of partial derivatives as well. Okay. So let's go back to this example of the circle that we just did. So let's do back to the circle problem. I had given you this F, which was X comma Y, right? And so this was like, in this notation, this is like what we're calling M. This is what we're calling N. Okay. And the circle was what, of radius 2, correct? So it was X squared plus Y squared equals 4, right? And so if you want to find the flux, now you can use Green's theorem. According to Green's theorem, there's an integral over the region R. Okay, and what's the partial derivative of M with respect to X? It's just 1, right? What's the partial derivative of N with respect to y is just 1. Right? So you have to do the integral of the function 2 or the constant 2 over the double integral over this disk. So how would you integrate this function?
Would it be polar coordinates?
Yeah, the easiest thing would be to do like polar. It's like, so remember, if you do the integral in polar, it's r d theta, right? Theta goes from 0 to 2 pi, and r goes from 0 to 2 in this case, right? So what's the integral of 2r? That's r squared, right? So you get like the integral from 0 to 2 pi of r squared, 0 to d theta, right? And so you get 4 times the integral from 0 to 2 pi of d theta. And so that's how you end up with 8 pi.
Wait, wouldn't it be 2r? Since
I'm integrating 2r, right?
okay,
Because-
so then it's r squared over 2, but then there's also the other 2.
Right.
Does that give,
Yeah, exactly.
but what about the one that's in the bounds for r from 0 to 2?
Oh, I use that to, I
Oh,
mean,
okay, yeah.
right, yeah. It became, r squared became 4, right? So.
Yep.
Yeah. Yeah, or if we want, I could put the 4, leave the 4 inside. So maybe that's easier. Yeah. Is that okay with everyone?
1 second. So we
Yeah.
had the 2 right there, and then we had the r. It became r squared. What happened to the 2?
So let me put it here. You have 2r, right?
Oh, okay. Got it.
Yeah. Or it's r squared over 2, but times 2, the 2's cancel. Right. Is that okay? So good. Well, it's more due to like lack of coordination, I guess, between courses. Like in many places, like a class that involves flux in physics does require multivariable calculus as an introduction, like as a prerequisite. So it is more like a question for the physicists, I suppose, than the mathematicians. But yeah. So maybe just to finish, like this is more or less 16.4. Like so, like the only section that's left for the exam is 16.5, which again we'll discuss after the break. Just to give you like a preview. Oh, good. Good to hear that. To give you a preview, like what we have to do, like next after the break, what will be to parameterize surfaces, not curves. Okay. So the difference will be that a parameterization of a surface uses 2 variables in the parameterization. Like a curve, remember? A curve uses 1 variable, uses 1 parameter t. And a surface will use 2 parameters. Usually they can be called u and v. So that's the difference between a surface and like parameterizing a surface and parameterizing a curve. So again, like we'll redo these examples next time, but let's just start with something easy for people to get a hold on what we're going to do. But imagine that I give you like the equation of a plane, right? So think of this plane like as a surface. So the plane has equation 2x minus y plus z equals 5. Okay, so like the idea of parameterizing a surface is that if you pick a point x comma y comma z on the surface, but the thing here, right, is that as you see, like at this moment you see 3 variables, and we don't want that. So the parameterization of a surface needs to somehow get rid of one of the variables, right? So how can you get rid of one of the variables in this example of the plane? Any thoughts?
You can write each one in terms of another.
Well, the most that we can do is write one of the variables in terms of the remaining 2, right? Exploiting the fact that we have the equation of the plane, right? So well, you cannot really make 1 0. Well, you have to, because like that would be like if you say that 1 is 0, it's like saying that like 1 is always 0 on the surface. That's not necessarily the case. But like, for example, yeah, you can write z in terms of x and y using the equation of the plane. And so then it gives you z equals 5 plus y minus 2x, right? And that's it. That's it. That's the parameterization of the plane in terms of x and y. So this is a parameterization of the plane Is that okay? But you could also say, well, but I don't like this parameterization. Like I want the variable z to continue there. So if you see, you can also say that 2x plus z minus 5 equals y. So an alternative parameterization is to get rid of y. So you get x and then y becomes 2x plus z minus 5. And then z is still z, right? And like the point is that this is like an alternative parameterization, but that's fine. So this is a parameterization which we would call r of x comma z, because like now x and z are the variables, right? So this is like an alternative parameterization of the same plane, right? Similar to how I did the parabola in my previous example in 2 ways, with x or with theta. Like this is like analogous to that. Is that making sense? So like the point, like the moral is that there are like different parameterizations available to you. It's not that there's only one parameterization you can use. Is that okay? So, and just to, again, like we'll do this a lot next week, but let's do another last example, and with this I'll finish. Imagine that I give you a cone, right? So this is the equation of a cone. So what's the parameters? What's one parameterization of the cone that you see almost immediately here that you could use? Yeah, in terms of x and y, and you just replace like, we'll get to that one with r in a second, but you can just replace z as a function of x and y, right? So this is the most obvious parameterization of the cone that you can use, right? So this is a parameterization in terms of x and y. But yeah, there are some fans of polar or cylindrical coordinates among you. So in polar, right, this becomes r cosine of theta, r sine of theta, z, right? But what does z become in polar coordinates on the cone? This is r, right? Z equals r for the cone, right? Because of the equation. So an alternative parameterization would be r cosine of theta, r sine of theta, comma r. Is that okay? And so this is a parameterization of the cone in terms of r and theta. Is that making sense? So essentially, like the idea is that a surface is given by some equation, and you use that equation to get rid of one of the variables, or just to rewrite them, to simplify, so that instead of having 3 variables, you only end up with 2. And the idea for what we're going to do that is that in next week, we will do integrals over a surface. So instead of integrating like a region on the XY plane, we will do like an integral over a cone. And for that, we need like a version of this Jacobian. And the version of the Jacobian requires like a parametrization of the surface. And so we're parameterizing surfaces so that we can do integrals over surfaces. But we'll talk about that on Thursday of next week. So enjoy your break. I'll see you Thursday of next week then. So, but if something comes up, feel free to email. But
Oh, one question, Professor.
yes.
So next week, Tuesday, no recitation, right?
Well,
Or-
no, I think actually, I don't think there will be a quiz. I'll think about it. Maybe not. Unless there's like, so that people enjoy their breaks. That's fine. I'll just give you like a list of recommended problems. But yeah, I mean, but I think there's nothing wrong with the calendar. So Tuesday is still Tuesday. So we'll have recitation, and if someone wants to show up for like, do practice problems or whatever, that's fine. But yeah, I guess it's fine. Let's not have a quiz next Tuesday. But there might be one. I have to double check. Definitely not on Monday. We don't have classes next Monday, but okay. Good. So that was my sharing. Happy Thanksgiving.